Welcome back as we continue our analysis of Romberg integration. This table represents the values we computed in the previous lesson. I have reproduced it here for convenience. Last time we were comparing these values to the exact value. The question arises, what if we don't know the exact value of the definite integral? Is there any way we can get an idea of how close our approximations are to the true value? The answer is yes, although, like anything, there are limitations. Take a look at the table up top. Same data we just saw, except I've underlined certain digits. Trace your eyes down each column to see the pattern. If a sequence of digits is the same from one row to the next, we have strong confidence our answer is converging on that true value. Notice as we move from one column to the next, we tend to see more digits underlined. This should make sense. If the rightmost columns are the highest order approximations, as we discussed last time, they should be more accurate than the lower order approximations on the left. In the bottom table, I have counted the number of underlined digits. This gives us a lower bound, a minimum number of digits of accuracy. Why a minimum? Take a look at this example. In case A, we have 5 matching digits, whereas case B has 0. Regardless of that, the error for case A is about 50,000 times greater than the error for case B. Why? Because 2.99995 is below the true value. 3.0 is above the true value. Due to rounding, the method we just used only works if the approximation is below the true value. This is an extreme example to illustrate a point. Normally, such a method can give us a good, rough idea of how accurate our approximation is. In fact, if we don't know the exact value, this could be the only way of knowing roughly how good our approximation is. It gives us an indication of whether or not our answer is converging on a value. This table was also produced in the last lesson. In the bottom, the absolute error is shown for each entry in the table above. Using this information, we can employ a better method of measuring how accurate our approximation is. Of course, this requires that we know the true value, which is not always the case. The trick is to take the base 10 logarithm of the absolute error, negative logarithm to get technical. Since we are using base 10 numbers, this effectively counts how many zeros are to the right of the decimal. I'm sure there are some questions on this step, so don't be shy to put them in the comments section below. If we round those numbers to the nearest whole number, we get the table in the bottom. So what does all this mean? If we round the values obtained from Romberg integration to the specified number of digits, it will match the true value, also rounded to the same number of digits. For example, the number shown is rounded to 9 digits. That matches the true value rounded to 9 digits. I leave the rest of them as an exercise for you to complete on your own. Do note, however, that because we rounded the logarithm up in some cases, our rounding could be off by a digit sometimes. We noted at the beginning of the lesson that our approximation becomes more accurate toward the bottom of each column. That makes sense. Decreasing mesh size tends to do that. It was also noted that accuracy tends to increase as we move right across a row. So, starting with this table of values once again, let us now find the most accurate approximation for a given number of rows. With only 2 rows, this is our most accurate approximation. Once again, we don't always have the luxury of knowing the true value to compare to. In this case we do, so we're going to take advantage of that. For 3 rows, this is our most accurate approximation. Again with 4 rows. Are you noticing a pattern yet? Same idea with 5 rows. So it appears the most accurate approximation for a given row is in the rightmost column. You may have observed the pattern earlier when looking at the absolute error. That's just a different way of demonstrating the same idea. Lastly, 6 rows. Don't forget these values we've boxed in red. We are going to tabulate them very shortly. This data came from previous lessons. Feel free to revisit them if you need a reminder of how to employ those methods to get these numbers. If I want to put all that data together and compare methods, it would look something like this. I did add a couple more rows for n equals 96 and n equals 192. I can also compute the absolute error for each box. What patterns do you observe? Which methods appear to converge more rapidly? Taking the negative base 10 logarithm of each absolute error, these numbers can be obtained. Rounding those logarithmic values to the nearest whole number gives me this data. Remember, this indicates how many digits of accuracy our approximation has compared to the true value. Which methods appear to be more accurate for a given mesh size? A picture truly is worth 1,000 words. If I plot the data from 2 slides ago, it would look something like this. This should make sense. The trapezoid rule is only second order, so it has fewer digits of accuracy than any other method. Romberg outperforms everything else by a significant margin. The other 3 methods are clustered pretty closely together in the middle. Here I have plotted the exact same data, except the x-axis is on a logarithmic scale instead of a linear one. Everything looks like a straight line, except the rightmost portion of Romberg integration. What's going on there? Why does it just flatten off? Well, remember that any software can only handle a finite number of digits. It appears as though we have hit that limit and maxed out around 16 digits. I won't go into the details here, but if we correct that misrepresentation, the graph should look more like this. So it appears that 192 panels with Romberg integration will give us closer to 18 digits of accuracy, not 16. Caution should always be taken when extrapolation of data is involved. That being said, we could extrapolate these graphs to estimate how many digits of accuracy we could obtain for a given method and number of function evaluations, n. That could give us a rough idea. That's about all the more I'm going to say for now. What do you think about all this? As we compare methods, what are the advantages and disadvantages of each one? Let us know in the comment section below. If you know someone else who could benefit from these lessons, I kindly ask you to share this with them. Your support is greatly appreciated. It is my goal to continue producing quality material for the enhancement of your appreciation of mathematics.